Swayam Prabha. Digital India. Educated India.
Welcome to this next lecture on vibrations of plates and shells. So we were looking at the response of a cylindrical shell, a curved structure, okay. And last class I mentioned to you that as it is closed in the theta direction, we will need two sets of modes, okay, to fully describe the displacement, okay. So we had seen this up till this point, okay. Now, so let us say set 1, we have set 1, okay. What are we going to substitute in the equations? So let us say the equations are like this: L1 operating on U1, U2, U3 minus lambda U1 dot minus rho h u1 double dot is equal to minus q1. This is the form the textbook uses, okay. So we are looking at natural frequencies, so this is, we will keep it undamped and unforced. So I have L1 u1 u2 u3 minus rho h u1 double dot is 0, then L2 u1 u2 u3 minus rho h u2 double dot is 0, okay. Then L3 u1 u2 u3 minus rho h u3 double dot is 0. The three equations are coupled because of curvature, okay. Now as I said, suppose we consider set 1, then how will it look like? U1 will look like AMN. So U1 and UX are same, okay. UX is U1, okay. So U1 U2 U3, or I will stick with the same notation. Let me stick with this. So we will say UX is equal to AMN or UXMN, sorry, UXMN is equal to AMN cos m pi x by L cos n theta, and we want natural frequency, so we set the time as e to the power j omega t. Then you have u theta mn as, let us say, b mn sin m pi x by L sin n theta e to the power j omega t. Then u3mn as some cmn sin m pi x by L cos n theta e to the power of j omega t. So we go ahead and substitute this into these equations, okay. So now the L1 is a spatial operator, it will operate on space. This is a temporal operator, it will operate on the time. Same here, same here. This is time, this is time, okay. As a result, what will happen is that because it is coupled, everywhere there will be AMN, BMN and CMN. Everywhere they will come, AMN, BMN and CMN. and because these are mode shapes, they exactly satisfy each equation, so they will fall out. They will fall out as a product. Okay, they will separate out so that we can remove them. So the differential equation becomes algebraic, that is the idea. Okay. So what happens now, if you do that, you will get a matrix now that looks like this. There will be some terms depending on E, rho, H, mu, etc. Then you will have rho H omega mn square here, and this will be A mn, B mn, C mn mode by mode, and this will be 0, and on the diagonal again some term rho plus rho H omega mn square, diagonal some other term plus rho H omega square mn, and there are terms here, not 0. Okay, there will be terms here. So now if you, in order to find the omega mn square, you have to take the determinant of this matrix, determinant. And for non-trivial solutions of AMN, BMN, CMN, the determinant is set to 0. So you will get a cubic in the square, you get a cubic in the square of omega mn square. Okay, so you will get a polynomial omega square into something plus omega mn square into something plus a constant. That is what you will get. Okay. So you will get 3 sets of resonances, 3 sets of omega mn. You will get omega mn 1 set, you will get omega mn second set, you will get omega mn third set. 3 sets of natural frequencies. Okay. Now suppose I pick one fellow from the omega mn 1 set. I pick one fellow, they are a list, right? M goes from 1 to infinity, n goes from 0 onwards. So there is a infinite number of resonances, well, just even the one, and I substitute it back in here. I substitute this number back in here. Okay, because it is a root, now the matrix goes to singular, becomes singular. Okay. As a result, what will happen is you can't solve AMN, BMN, CMN independently. You will have to solve one in terms of the other. So maybe you take CMN is equal to 1, then you solve AMN, or rather AMN by CMN, CMN is 1, then you get BMN by CMN. Okay. Okay. So now it may turn out, okay, it may turn out that AMN by CMN is very large, very large. Okay. In other words, you should try rather AMN as 1, then BMN by AMN and CMN by AMN. Okay. So now it may turn out that AMN is of course 1, but BMN by AMN is very small, and CMN by AMN is also very small. That means the AMN is a big number compared to the others. That means based on this expression, these are negligible. BMN is small, this is negligible, this is negligible, this is dominant. That means what? The first set of natural frequencies describe dominantly axial motion, axial modes and resonances. and resonances. Okay. So, omega mn1 set of modes, natural frequencies describe where the shell point, a point on the shell, is dominantly moving axially. It is also moving torsionally, it is also moving radially, but its dominant movement is this slight amount of theta movement, slight amount of vertical movement. Okay. Dominantly its x direction movement. Okay. Now the shell is quite stiff in the axial direction, okay, compared to the other two directions it is quite stiff. Okay. So these frequencies are high or very high, high frequency values. These natural frequencies are high or higher. Okay. Similarly, if you pick one fellow from the second set of natural frequencies, you plug it in here, again this matrix becomes singular, and then you may find that you are looking at Bmn is equal to 1, then you have Amn by Bmn and Cmn by Bmn. It may turn out that Amn by Bmn is a small quantity, similarly Cmn by Bmn is a small quantity, and this is about 1. Okay. Now what that would mean in terms of this description is that Bmn is dominant, Amn is small and Cmn is small. So these set of natural frequencies are describing the torsional motion or dominantly torsional motion. Okay. So these describe dominantly torsion. They are also high but next to the axial. They are also higher frequencies. Okay. Now the last set. So if you do this, you will find that you look at Amn by Cmn and Bmn by Cmn. These will be small quantities. Okay. And then Cmn will be of order 1. Then these are dominantly radial or transverse or flexural, as we call it, flexural, that is bending dominated, flexural, transverse, radial displacement, natural frequencies. Okay. So in these frequencies the shell is moving radially outward dominantly, even though it could have a slight torsional movement and axial movement. Okay. That's how the natural frequencies pan out for a curved shell because of coupling. Okay. So that is the other point. Now the last point I want to make about shells is that with respect to the radial movement or transverse movement, radial movement, okay, if we look at the circumferential behavior, that means with respect to n, the index n. Okay. So how does n equal to 0 behavior look like? If n equal to 0, okay, so you can see here that this goes to 1. There is no theta dependence. Okay. So that means what? If I have a nominal initial radius, it uniformly expands without theta dependence and uniformly contracts without theta dependence. Okay. This is in one part of the cycle and this is in the other part of the cycle. This is n equal to 0 movement. Okay. So, there is a lot of stretching as we call it. Okay. The shell stretches and that is how you get a, now this is like a breathe, this is called the breathing mode. Breathing mode. Like you breathe and your chest cavity uniformly expands. Okay. And there is hardly any bending, no bending. The shell element is not bending. Okay. There is no bending happening, no bending happening. Okay. So, if I go to n equal to 2, okay, just taking a higher mode number in the circumference, then if this happens to be my nominal circle, then n2 behaves like this. It in part of the cycle it acquires this shape, in another part it acquires this shape. Okay. So, you can see that some stretching is there is some stretching and some bending. The shell element is flexing a little bit and stretching a little bit. Okay. So, if I go to n equal to 4, let us say n equal to 4, then if this is my nominal, let us say this is my nominal diameter, then the shell at some point will look like this. Messed it a little bit. Okay. So, yeah, something like that. Okay. More symmetric, but so you can see that there is lot more bending, a lot of bending, and hardly any stretching, less stretching. Okay. So, now if we think of the Rayleigh quotient, if we think about the Rayleigh quotient, it has strain energy and it has the kinetic energy, which is proportional to omega mn squared. Okay. Now, you can see that a higher order mode will have higher strain energy, okay, and hence correspondingly higher kinetic energy. That is how you get a balance. Okay. And therefore, this number is higher, this natural frequency number is higher wherever there is higher strain energy. So, you can get the amount of strain energy, you can get a feel for where the natural frequency can lie. Okay. Now, let us look at the strain energy in stretching. Strain energy can be broken into stretching energy and bending energy. Bending energy. So this is also called membrane energy or membrane stretching. So if I now kind of plot or locate n equal to 1, n equal to 2, n equal to 3, n equal to 4, etc., and 5, maybe I need a few, equal to 5, etc. So if I look at n equal to 0 mode, there is a lot of stretching energy, strain energy due to membrane stretching. Okay, and we will say that there is not much, red will be bending, there is not much of bending. Okay, I did not show the n equal to 1, but n equal to 1 will have a little less, I will make it dramatic to get a picture, a little less stretching and a little bit more bending. Next, in n equal to 2, there is a little further less stretching and a little bit more bending. Okay. Similarly, with respect to others, stretching reduces and bending takes hold, more and more bending happens, more and more bending. Oh. Okay. So now these are energies, okay, they are strain energies. So if we add up, if we add this up, what will happen is you will get a picture that looks like this. Get a picture that looks like this. The net picture looks like this. Okay. So the natural frequency curve, the flexural natural frequency curve, okay, they have this dip, in the natural frequency. So the n0 will start off higher, there will be some n which will be low, and then it starts to rise again. Okay. So maybe along these lines I will tell you something practical. Okay, we have been at theory for a long time, so I will tell you something. So if you have a long aspect ratio shell, that means the shell length is long, let us say, okay, and then compared to the radius, then what happens is that I will tell you the picture looks like this. So you will start off somewhere here, then there is a shallow, very shallow dip. That means the dip lasts for a long time and then starts to rise. This is n equal to 0 and this is m equal to 1. You have two indices. Then for m equal to 2, so let me, these are the n points, okay. Then if you take m equal to 2, then it is going to be very close because of the aspect ratio, it is going to be close. The m2 natural frequencies are very close, they will be higher but close. Okay, that means their circles are here. This is n1, n2, etc. Then m3 maybe slightly above and but again close. And 4 is close. Okay. Now that means what? That means it at any frequency, suppose this is some 100 hertz or so, then there are that many modes that are close to 100 hertz which are low order modes, and there are, if I extend this line, then again there are so many modes close to 100 hertz. These are higher order modes. Okay. Now if we consider an aircraft shell, and let us say we consider a shell, the body fuselage as, okay, then this body we can consider approximately as a cylindrical shell with a long aspect ratio. Okay. So here, and then we have the engine, over here. Okay. Now the engine will have blades. So let us say hypothetically it is rotating at 3000 rpm, okay, which is 3000 by 60, which is 50 hertz. The shaft rotor is going at 50 hertz, and let us say there are 4 blades, then you have 200 hertz. Okay. So now at 200 hertz you will have air being pushed towards your fuselage. Okay. So if you happen to be sitting in the propeller plane, engine plane, okay, inside the aircraft, or approximately left forward or behind, then you will hear this hum in your ear. Okay, you will hear the engine hum, and it can be bad, it can be really bad. Okay. So now you have to control or reduce noise inside the aircraft. You have to control or reduce noise inside the aircraft. Okay, it's a noise control problem. Okay. But now if you, so now what happens is that largely these lower order modes are responsible for transmitting the sound into the shell. These set of modes get excited. So let us say instead of 100 this is 200 now. Okay. So now around 200 hertz there are that many modes. You could have 100 modes. Okay. So that many modes are now responsible for transmitting. That means the shell vibrates. This shell vibrates now. This is shell vibrations, and the vibrations in turn send sound inside the cabin. Okay. But suppose now you have some strategy of reducing these modes. Okay. By some active means, by you put shakers or you put acoustic speakers inside the cabin and do it, try to reduce it. Now nature is not very forgiving. Okay. So you may be able to either attack the structure and reduce these lower order modes, reduce their amplitude, okay, thereby reducing noise. But because the frequency is same for the higher order modes also, when I try to reduce these lower order modes, these higher order modes will get excited more. You do not get a double benefit. Okay. And the reason is that you are tackling, your excitation is around 200 hertz to reduce that 200 hertz sound. So around 200 hertz there are so many resonances, so they will go up. So that means the aircraft shell will go into vibrations. and will cause fatigue. It is not good. Okay. And why is this lower order higher order headache happening? Because there is this dip. Why is this dip happening? Because there is a coupling between membrane and bending, because it is a curved shell. So this is kind of inevitable if you have curvature. Okay. You remember your plate resonances, they will go high and they will taper off. They do not go through a dip if you plot your natural frequencies for a plate. Okay. They do not go through this dip, it is a flat structure. Okay. So I just wanted to mention that how this dip creates a problem with respect to noise control in aircraft cabins. Okay. So now we have to look at the response to a point force. Okay. So we are going to do it modally using modal summation. Okay. So one set. So we said there are two sets of modes. So set 1 we will call it as UX set 1 x comma theta comma t, okay, is equal to what? Is equal to now the summation, okay, over I goes from 1 to 3. These are the 3 sets of natural frequencies. 3 sets of natural frequencies. Because there are 3 kinds. First is dominantly axial, second is dominantly torsional, third is dominantly flexural. You have 3 sets. Then you have the m set of mode numbers, the n set of mode numbers going from 0 onwards. Then we have the participation factor with time, and then the component of the mode shape in x direction, which is function of x comma theta. Okay. So if I have to write this, I would write it as a m n I divided by c m n I cos m pi x by L cos n theta. Just this bit. Okay. Then the u theta movement for the first set x comma theta comma t is now again a summation for I 1 comma 2 comma 3, okay, summation over m, summation over n index going from 0, m going from 1, the same modal participation factor eta mn. Why? Together I will tell you, okay, it is the same mode. So then u theta mn x comma theta b mn I by c mn I sin m pi x by L sin n theta. Okay. Then lastly u3 first set x comma theta comma t summation over I, summation over m from 1, summation over n from 0, eta mn of t u3 mn x comma theta, where u3 mn is sin m pi x by L cos n theta. okay, and this is one mode, this together is one mode, this together is one mode, okay. If I is 1, I is equal to 1, this is the axial mode, axial mth mode. If I is 2, this I is 2, this is the torsional mth mode, and I is 3, this is the transverse or radial mth mode, okay. So, because this is one mode, therefore, the same modal participation factor, same modal participation factor, okay. So, now if I do set 2 if I do, then this will be sin n theta, this will be minus into minus cos n theta, and this will be sin n theta, that will be set 2, the rest will remain same, okay. So if we have to find a response to a point force, okay, then what we will have to do is find it for set 1, find it for set 2, and then sum them up, okay. So we are now running out of time, so what I will do is I will stop here and we will continue this discussion in the next class.